You are conducting a right-tailed test of a claim about a population mean when sigma is unknown with a sample size of 23. If alpha equals 0.025, find the critical value to 2 decimal places. Using the hypothesis testing guide, we can think through the steps of how to find the right critical value. We don't need to complete everything in the form, but just going through the first few steps will help. So we want to set up the hypothesis test, and it's already been told to us that it's right-tailed, and it's a claim about a population mean. So I know to use the Greek letter mu, and that this is a right-tailed test. Now, since I'm doing a claim about a mean, it's possible that my sampling distribution will be z-scores or t-scores. If sigma is unknown, we use the t-distribution. So the sampling distribution for this would be the t-distribution. That means that the critical value I'm trying to find will be a t-score. Now I can do a quick sketch of the test to help me along with the rest of this problem. A critical value on the right side of the center, that is a t-score, will be positive, and we just need to figure out what that boundary is. We need an area to help us with that. The area to the right of the critical value is the significance level. The reason it's to the right is because the significance level will always be in the tail, the small tail. And since our t-score is on the right side, it makes sense that we'll have the significance level on the right. The area on the other side is 1 minus alpha, or 1 minus 0.025. And I'll need that area because I'm going to use t inverse in Excel to find the t-score. And t inverse always needs you to give it a left area. So my significance level of 0.025 in the right tail will give me a left area of 1 minus 0.025. And my t-score, which is my critical value, will be positive, and the value will be found using t dot inverse with my left area, and I also need the degrees of freedom. The degrees of freedom for a t-test is n minus 1. So n minus 1 would be 23 in this case, minus 1 is 22. Making sure that this is positive, just as an extra final check. I know since it's supposed to be on the right, it must be positive. And it says to round it to 2 decimal places, so I have 2.07. Here's another example where we're conducting a left-tailed test. And they've given us a different significance level. And other than that, it's the same question. We're conducting a left-tailed test of a claim about a population mean when sigma is known. Oh, that's also a change. Remember, sigma was unknown in the last one. So we've got a couple different things to consider here. I'm going to go back up to the top here. And I'm still doing a test about a mean, but sigma is known, so this is going to be a z-test, or a standard normal distribution. And the test this time is left-tailed. So again, my area will be all in one tail, and it'll be 0.1 this time. And the left area is equal to, well, actually the left area is alpha, because now that I'm doing a left-tailed test, I'm going to have a critical value on the left side of the curve, and the area will be in the small tail. So let's look at the sketch of that. Okay, so our sketch has the critical value on the left side this time, and it's a z-score, a negative z-score. It's negative because it's on the left, and it's a z-score because sigma is known this time. The area in the small tail is your significance level, 0.10. And just as I needed a left area for using the inverse t function, I'm going to need a left area again using the norm inverse function. And since this is a left-tailed test, I don't have to subtract my significance level from 1 this time. So my z-score is negative, and I'll find it by using norm.inverse with the left area and then a mean and a standard deviation. Because I'm looking for a z-score, and z-scores are the boundaries of a standard normal distribution, the standard normal distribution always has a mean of 0 and a standard deviation of 1. And so there I have my value, and rounded to 2 decimal places would be negative 1.28. And here we have another similar example. Let's see what's changed in this one. You are conducting a left-tailed test of a claim about a population proportion. That's new. Before we were doing claims about means. So a population proportion means the parameter symbol will be p, and this is going to be it says a left-tailed test. And since it's a claim about a proportion, we will be using z-scores. Now to find my critical value, doing a sketch will help me think through what I need to do. Again, I have a left-tailed test with a z-score, and the area this time is 0.005, and the entire area is in one tail. So changing this to 0.005, that will be the left area that I need to feed into the norm.inverse formula to get my z-score. So here, my area of 0.005, my significance level, will also be my left area. I don't have to subtract it from 1. The distribution is the standard normal distribution with z-scores. And since it's on the left, this will be negative. And now I'm using norm.inverse again with a left area of 0.005, a mean of 0, and a standard deviation of 1. Rounded to 2 decimal places. There we are. All right, now this example, let's see what's changed. We're conducting a right-tailed test of a claim about a population proportion. Okay, so what's changed here from the last example is that this is a right-tailed test, and also the significance level is different. But it is still a claim about a proportion, so we will still be using the z distribution to find our critical value. So the area, 0.01, this time is not my left area because this is going to be a right-tailed test. So knowing that I'm looking for a z-score that will be positive with an area in the small tail of 0.01, then my left area will be 1 minus 0.01, or 0.99. So here in my table, or my form, putting in 0.01 gives me a left area of 1 minus 0.01. The distribution is the z distribution because it's a claim about a proportion. It's on the right side, so it'll be positive. And the value will be found using norm.inverse with my left area, my mean of 0, and my standard deviation of 1. Rounded to 2 decimal places, that's 2.33. And here we have a two-tailed test of a claim about a population proportion with alpha 0.2. Find the positive critical value to 2 decimal places. All right, so let's see. What's changed from the last example? We have a two-tailed test. We are still doing a claim about a proportion, so the p stays the same. We are still using the z distribution, since we always do when testing claims about proportions. So the main thing that's changed is that now we have 2 tails instead of 1. So in our sketch, we're going to split up our alpha into 2 tails. Some over here. So that'll be half of the 0.2. So half of 0.2 is 0.1. So that'll give me my positive critical value, which is a z-score, and my negative critical value will have an area to its left of 0.1. So now, if I find this left, or rather, I'm not finding the area, I know the area, this left boundary, then I'll know that its twin, which is just positive, will have the same absolute value. So, to make this simple, my area, or my total significance, is 0.2. But the area in the left tail is only half of that. So using norm.inverse on my left area, I will get the negative version of my critical value. And I was supposed to give the positive. It asked specifically for the positive critical value. So all I need to do when I type this in is just make sure not to include the negative sign.